Hello viewers, my name is Mr. Kazim and I am delighted to welcome you to my YouTube channel at Smart Edu TV. Here you will find detailed tutorials on your science courses and tips on how to answer examination questions successfully. I started this channel to also share my knowledge and experience in this field and to give you tips on how to succeed as a university student. If you are looking for detailed tutorials on physics subjects, chemistry, mathematics, biology, statistics, and the general studies (GST), then you have come to the right channel. So therefore, sit back, relax, and join me on this journey. Don't forget to hit the subscribe button and turn on the notification bell to never miss on an important update. Please remember to also share this video so that others can benefit. Thank you very much.
Okay, hello viewers, you are welcome back to our channel. Today we'll be looking at isomerism in organic chemistry. And before then, the importance of chemical formulas in organic chemistry cannot be overemphasized. Two of such formulas are the molecular formula and the empirical formula. Let's look at this ethanol for an example. We have the formula for ethanol as CH3 CH2OH. When you look at this, we have two carbon atoms, so C2. When we look at the number of hydrogen, we have 6. And when we look at the number of oxygen, there is only 1. So writing formula like this is referred to as molecular formula, while the first one is referred to as a structural formula. Likewise, let's look at another one. So this one is CH3OCH3. Once again, if you look at the number of carbon, 2, number of hydrogen, 6, and number of oxygen, 1. The two of them we have written the structural and the molecular formulas for both of them, ethanol and methoxymethane. But we realize that the two of them have the same molecular formula, even though the structural formulas are different. So this phenomenon is referred to as isomerism. So isomerism, by definition, is the existence of two or more compounds. In this case, you have only shown two. The existence of two or more compounds having different structural formulas but the same molecular formula. So today we want to look at the concept of isomerism. So in this case, we are going to classify the different types of isomerism and we give examples of these ones. Okay. The chart shows the different types of the isomerism that we have and how they are broadly classified into two. Though, aside these ones, we still have some which are not relevant in this elementary aspect of isomerism. Broadly speaking, isomerism classified into two: the structural isomerism and the stereoisomerism. We're going to discuss the differences between the two of them. But on the chart, we can see that the structural isomerism is further classified into 5 types: the chain isomerism, position isomerism, functional group isomerism, metamerism, and tautomerism. On the other hand, we are going to look at only 2 types of stereoisomerism: the cis-trans isomerism, also known as geometrical isomerism, and the optical isomerism. So before we look at each of these types, let us look at the 2 major classes of isomerism. Oops. Okay, the first class of isomerism, as we mentioned earlier, is structural isomerism. It is also known as constitutional isomerism, and it's a type of isomerism that explains the differences in how the atoms of the compound in questions are linked to one another. For example, there are five atoms here in this structure, but you can see that the atom 1 is connected to atom 2, connected to 3 and 4. But atom 5 only connects to the third atom. If we have another one in which instead of that connection, we have it in this, it is obvious that there are two structures. In the first one, atom 5 is connected to atom 3, whereas atom 5 is connected to atom 2. So the two of them are said to exhibit structural isomerism. The structural isomers differ in the ways the atoms are connected to one another in the compounds that are under review. In the second class, which is stereoisomerism, we can see the two structures. If we look at it from the angle of structural isomerism, we can see that A1 is connected to A2, to A3, to A4, and to A5 in the same way for both structures. But what makes it different is the arrangement of the atoms in space. In the first one, we can see that A1 and A5 are at the same side of the plane, whereas in the second one, they are at the opposite sides of the plane. So we can see it, A1 is here and A5 here, below the plane and above the plane. But here, both A1 and A5 are above the plane. So in stereoisomerism, this is a type of isomerism in which the atoms have different arrangements in space, though they are connected to one another in the same way. So, as mentioned earlier, there are five types of structural isomerism, and the first one we are going to look at is the position isomerism. By the position isomerism, we mean that the structures under review differ in the positions of a branch or substituents. Let's look at this one now. Bromine is a substituent here and it occurs at the first carbon, while it is located at the second carbon here. So in this case, we said that the two structures here exhibit position isomerism. We are not interested in their names. However, this one is called 1-bromopropane, while this one is called 2-bromopropane. For now, our attention is not on the names, but rather on the existence of isomerism in them, so that we can readily identify that this one and this ones are different structures based on the positions of the bromine. Another, okay. In the second example, we can see that the branch occurs at the second carbon here, whereas the branch occurs at the third carbon. So this is another example of a pair of position isomerism. As we said earlier, it can be due to the positions of the substituents or due to the position of a branch. So lastly, we can also see that the two compounds have different positions of the functional group OH. In both cases, like we said earlier, this one is at the terminal carbon, while this one is located at the non-terminal carbon. In other words, this one is at the first one, while this one is at the second carbon. So all these ones are examples of position isomers. I hope that you'll be able to quickly recognize position isomers when you cite them. In the second example, in the second type of structural isomerism, we have chain isomerism. And for you to quickly identify them, we have two types of chains. we have the straight chain. An example is this one, and we have the branched chain. An example is this. You can see is that each structure has 4 carbon atoms. 1, 2, 3, 4. 1, 2, 3, 4. But as we even counted it, this one is a straight chain. 1, 2, 3, 4 on a straight form. And why this one? 1, 2, 3, and there is a branch here. So we call it a branched chain. So these two types are called chain isomers. So chain isomers can be straight chain or branched chain. In this case, we have shown an example of C4H10. And we can see that there are two types of chain isomers for our C4H10. Normally, the straight one is what we used to call N. Whenever you see a compound name that has N, N standing for the normal, it means you are dealing with the straight chain. But if it is branching, there are various names that we use for them, such as iso, neo, tat, and sip. All these ones are discussing about the branched chain. Okay, I can start. Another example of chain isomers is the one exhibited by molecular formula C5H12. We can see the three structures. This one is the straight chain. So 1, 2, 3, 4, 5 straight chain. Why these ones are branched chain? You can see one branch here, but you can notice two branches here. So we say that they exhibit chain isomerism. So the first one is a straight chain isomer, while the remaining two are branching isomers. In the third type of structural isomerism, which is the functional group isomerism, you will recall that in the beginning of the class, we used these two examples. But for the first time, we are using compounds having different functional groups. So this one belongs to the alkyl functional group, while this one belongs to the alkoxy-alkane, also called eta functional group. So in the previous two examples we listed, under the chain isomerism as well as under position isomerism, the compounds we use belong to the same functional group. But for the first time, the compounds in use, they belong to different functional groups. And we say that they exhibit functional group isomerism. And we call them functional group isomers. In the fourth type of structural isomerism is what we call metamerism or radical group isomerism. Let's look at these two examples to understand metamers. In the metamers, the radicals are distributed in different ratios. For example, this is an ethyl radical and likewise this one. So this one is ratio 2 to 2. Now let's look at what we have here. This is ratio 1 to 3. So when there is difference in the distribution of the alkyl groups, we say that they exhibit metamerism and we call them metamers or radical group isomers. So in the first one, the alkyl groups, as you can see, it contains 2 carbon called ethyl, and this also contains 2 carbon called ethyl. So in this case, we say that we have 2 carbon ratio 2 carbon. But look at this one. This is methyl 1 carbon, while this one is propyl 3 carbon atoms. So in this case, we see that the distribution is in the ratio 1 to 3. So when we are having distributions of the alkyl groups in different ways, we say that they exhibit metamerism and we call them radical group isomerisms. For example, the one we have shown so far is within the eta groups. We also have, this is eta, they also exist in ketones. And we can even have them in they exhibit metamerism. So you should try to see beyond the ethers, because you can also have them in ketones on the ethers alone, also on the ketones and thioethers. The last type of structural isomerism is tautomerism. In tautomerism, the functional groups in question are in dynamic equilibrium. They are interchanging from one form to another, and that is the meaning of this symbol, equilibrium. So this one is called keto form of the isomer, while this one is called enol form of the isomer. Enol because it contains alkene and alkanol, what you can call alkenol. So the two functional groups are interconverting from one form to another. So, and we can call it tautomerism. We said the two of them are ketoenol tautomers. It's a special case because they are interconverting from one form to another. Otherwise, we could have called them functional group isomerism. But because they do convert from one form to another, it has a special class or a special case which is called tautomerism. That is the end of the structural isomerism. In the next one, we will try to list some examples so that you can identify what they are and what they are not. Okay, you can see this table. This is your own exercise. You have to tell us what type of isomerism is exhibited by each pair of isomerism. Compound 1, compound 2, the type of isomerism, likewise in the remaining 3. So you should pause and do it yourself, after which you can play it again so that you can see the answers. In our previous topic, when we are showing structures, this is a line structure. Don't forget that this one has a carbon here, there is another carbon, and here, making everything to be 5. Just a reminder of what we did. This structure or this one, you can try to lay it out in this way and you still get the same answer. For example, if I want to draw this structure, I can just say that C, there is one carbon here, then to another carbon, then to another carbon, then to another carbon, and finally to the last carbon. But in this fourth one, we can see a double bond with O. While in the remaining ones, just fill the number of the hydrogen. Since that this carbon has one hydrogen, in order to complete its tetravalent nature, then it will have 3 hydrogen. While this one has 2 already, it will have 2. This one has 2, it will have 2. This one is completed, it will not have any hydrogen. While this one has only 1, it will have 3. So at the end, we are having CH3, CH2, CH2, CO, CH3. So this is just a reminder of what we did in our previous class, so that you can actually be able to do this. But if you are already used to it, you can readily tell us the type of isomerism that these ones are exhibiting, likewise in which these ones are exhibiting. Once again, pause and try to put in the types. When you are done, you can play on to see the answers. Okay, I hope that you have done your own. So let us look at the answers and you compare it to what you have done earlier. So in the first pair, we can see that the number of carbon in each is 3. 1, 2, 3 in each. But we have an amino group attached to the terminal carbon here, or what you can call first carbon. And we have our amino group attached to the second carbon. So in this case, since that the position of amino group differs in both of them, So we can say that they exhibit position isomerism. In the second one, once again, if we lay it down, we can see that the first structure 1, 2, 3, 4, 5 with no branch, straight chain 1, 2, 3, 4, 5. And if I want to count this, it's either I move 1, 2, 3, 4 and there is a branch, or I move this way 1, 2, 3, 4 and there is a branch here. So either you call this one the branch or you call this one the branch. So this one is a branch chain isomer, while this one is a straight chain isomer. For this reason, we say both of them exhibit chain isomerism. Chain isomerism. In the third one, we can notice that the first one have first carbon here, second carbon here before the ketone group, and here first carbon, second carbon because after the ketone group. We can say the alkyl groups here is ethyl, while the alkyl group here is also ethyl. Now let's look at this one. 1, 2, 3 before the ketone group. 1, 2, 3. So propyl group C3, while this one is methyl group C1. So the alkyl groups are distributed differently. Here 2:2 and here 3:1. So because of that, we say that they exhibit metamerism. In the last example, it is obvious that the two of them belong to different functional groups. This one is a ketone group, while this one is the aldehyde group. In our previous class, we had introduced different types of functional groups. So this one is our ketone group, while this one is our aldehyde group. And for this reason, we say that they exhibit functional group isomerism. So that is the end of structural isomerism. In our next class, we'll be discussing position isomerism.